Hello everyone, welcome back to Bytes of CSE. So in this lecture, we'll be learning about the basic computational model of a multi-layered perceptron for deep learning. So as you can see in this example figure, it is a fully connected feed-forward network which has 3 nodes in the input layer and 3 nodes in the hidden layer and 2 nodes in the output layer. Now your hidden layer can contain 4 nodes or 2 nodes or even any number of nodes. It does not depend on how many inputs you have, how many input nodes you have in the input layer. So according to this diagram, there are 3 features. Since there are 3 nodes, it indicates that there are 3 features in your training example and there are 2 outputs. So before we get to understand the basic computational model, let us learn very briefly some matrix multiplication essentials which will be needed in this video lecture. Suppose you have 2 matrices A and B. So this has got 2 rows and 3 columns, and this has got 3 rows and 3 columns. So this gives rise to a C matrix. Now how to find the value of a particular C element at any position. Suppose we are trying to find out the value of say C11. So in this case, for C11, you have to consider this row number, or the first the number 1. You have to consider the first row of your left hand side matrix, that is matrix number A, and that is matrix name A, sorry, and you have to consider the first column of the matrix B. Now you have to multiply the corresponding elements, that is A11 will get multiplied with B11, A12 will get multiplied with B21 and A13 will get multiplied with B31, and you have to take a summation of them. Or in other words, this is what you are supposed to do in order to find any element. So for any element, say you are taking an element Cij, where I is your row number and j is your column number, you have to consider the ith row of your A matrix and the jth column of your B matrix. And basically, if I have to use a formula, you will multiply Aij with Bji, and this j value will vary from 1 to the total number of columns your C matrix will have. So in this case, as you can see, say A12 is multiplied with B21. So this is your I value and this is your J value. So in this case, the I values are same, and see, this is the corresponding J value. So Aij into Bji, again A13 with B31. And that brings me to another condition which you will be needing to know about matrix multiplication is, say you have a real number matrix of dimension m cross n, where m stands for the number of rows and n stands for the number of columns, and you're trying to multiply that with another real number matrix B which has h rows and t columns. So in order that A can be multiplied with B, the number of columns in your A matrix needs to be equals to the number of rows in your B matrix. Or in other words, your N is supposed to be equals to H. Now, if I multiply this A matrix with B, now see, I have replaced the value of H with N in this particular step, because n has to be equals to h in order that two matrices be multipliable with each other. So if they the resultant, if that be a C matrix will have a dimension of m cross t, that it will have m rows and t columns. So it's nothing like you will take the number of rows from your left hand side matrix, and you will consider the number of columns from your right hand side matrix, that is B matrix, and that will give you the dimension of the. Okay, now let's move back to our example. So we were considering a fully connected feed-forward network. Now let us feed n examples into this network. Now we said that there are three features in your input, in your example, and say each example be denoted as a vector containing these three features. Now in order to actually compute the now let's get back to the fully connected feed-forward network that we used in the previous like when we started this video. Now as we said before, let's blah blah blah. Okay, now let's get back to the example neural network that we started with. That was a fully connected feed-forward network. Now let us feed n examples into this network. As we said before, that the input there are three features in your example. So let us denote each example as a vector that contains those features. So this is your one example, and we will be considering all the n examples together for ease of computation. As a result, we will be constructing a matrix where we will be placing each of these vectors one after the other. So this is for your example 1. So this row of this matrix represents your example 1, this row represents your example 2, and this row represents your nth example. So as a result, since it has n rows, it will have since it has n examples, it will have n rows, and since there are three features, it will have 3 columns. Suppose you are to, like, if this xn2, if you're trying to find out what this xn2 is, now xn2 represents the second column of your, the second feature of your nth example. Now more generally, if we have to denote this X matrix, which is also known as the feature matrix, we will denote it as a matrix containing real numbers of dimension n cross d, where n is the number of examples or the number of rows is equals to the number of examples, and the number of columns, or this d, represents the number of features in each of your example. Now let's move on to the second layer, which is the hidden layer. Now coincidentally, as I mentioned before, it has got 3 nodes in your hidden layers. It can contain 1 node or even 100 nodes. That depends. Okay. Now each of these nodes in your hidden layer contains weights, and that weights are to be multiplied with each of the features of this example. Now the number of weights that each hidden layer will contain will depend upon the number of features, because naturally your weights will be multiplied to the features, so the number of weights will be equal to the number of features. So if I have to represent that as a vector, each node of your hidden layer will contain a weight vector like this, W1, W2 and W3, and here also we will be considering the matrix. But here what happens is, since the number of columns of your X matrix needs to be equal to the number of rows in your weight matrix, that is this W matrix, we are going to take a transpose of your weight matrix. So what happens is, in this transpose, the number of columns of your X matrix becomes equals to the number of rows of your weight matrix, and we are going to place these the transposed weight matrix of each hidden layer side by side to create your weight matrix. So in this case, each column will be signifying the each node of the hidden layer. So this is for the first hidden node, this is for the second hidden node, and this will be for the third hidden node. So here W22 or W32 rather, we take W32 will signify the third weight of your second hidden element. So now as you can see in this case, the weight matrix will naturally have a dimension of D cross M, where D is the number of weights which is equals to the number of features, and M is the number of hidden elements in your matrix. Now we have taken a more general matrix where X is a matrix of dimension n cross D. As you can see that this if we consider the last row, this is the nth, the example of your what you have fed. This is the nth example, and this is the dth feature. And then we have the weight matrix, which has a dimension of D cross H. H is the number of hidden elements. So WDH, it means that is that for the hth processing element, this is the dth weight element. And now we have another thing which is known as a bias. So bias is nothing but these are actually some constants, and each hidden element will contain one bias. So as a result, we are actually taking a transpose of that bias matrix too. So each row corresponds to one hidden element, and thus bias is basically H cross 1 matrix. So we are at this layer, okay? At this layer, we are still doing the processing. So this layer will output an H matrix, which will be equivalent to X into W1 plus B. So this had X as the output, and this layer will have H as the output. So in this case, as you can see that X is n cross G and W is D cross H. Therefore, H matrix will be of dimension n cross H, right? Now, this is fed into this layer. Now, your output layer also contains weights, and there are two processing elements in your output layer as in this example. So your weight matrix of this layer will be having a dimension of say H cross 2. That is, there will be two columns, each corresponding to one element of your output layer. So these equations, as you can see, are very similar. In place of X, now it contains H. Now H is of dimension n cross H. So from here you can guess that this W2 will have H as the number of rows, and for the number of columns it will be equal to the number of elements, that is the processing elements in the output layer. Say that number of elements be Q. So your W2 will be of a dimension H cross Q. And similarly, it also contains bias, and bias will be like one bias for each processing element. So this will be of dimension Q cross 1. So far what we have seen is, well, we have done so many things, but whatever we have found as an output, it is but an affine transformation or just a linear function. But as we know that our real world problems are seldom linear. So how do we add this non-linearity into our system? So this is added with the help of the activation function, say sigma. So now what happens here is, after you have computed this one, this layer, this H, now H, the activation function sigma works upon H. This is nothing but your H as you had computed here. Say this is H prime. So you might say that this is equivalent to sigma H prime. Now this activation function acts on each and every element of your H prime, like this vector, and now this activation function as non-linearity. Now I will be doing a separate video on this activation function, like what are the types of activation functions that are generally used in deep learning. But this is just for your information. Say this is your like hidden layered matrix. Say we are considering this particular element. Say this has a value of 0.23. Now maybe we have fed an activation function which says that if the particular value of a particular position be less than 0.5, we consider that to be equivalent to 0. So your 0.23 here, after going through that activation function, this value transforms to 0. So this adds some non-linearity into your system, and now this H, that is the H that you get after applying the activation function, is now fed as input to your output function. Now you might be wondering that is there only just one layer in your hidden like only one layer of processing elements in your hidden layer? No, there might be more than one processing elements in your one layer of processing elements in your hidden layer. So in this case, it works in the same manner. Like this hidden element, maybe you have another set of hidden elements over here. So what happens is that say this be H1. Now in this case, this H1, instead of adding to instead of feeding as instead of being fed as input to this output layer, it is fed into this layer, and this layer will, each processing elements of this layer will also contains weight, and those the dimension of those weight and bias will be according to the number of columns of this hidden layer and also the number of processing elements. And after going through all the subsequent layers, finally it will the final output, the final age of all the outputs will be, sorry, the final age of this hidden layer, that is the final layer of this hidden layer, will be fed as input into your output layer, and from there you will compute the output. So this is your final result. So this is how the computation is carried out in multi-layer perceptron. So we will be learning about activation function in our subsequent videos, and also some more details that we need to know about multi-layer perceptron. So that was all for today. Thank you. Thanks for watching.